Welcome to the presentation of Bayesian adversarial human motion synthesis. My name is Rui Zhao. Modeling human pose is important for understanding human motion, which has a long-standing interest within computer vision community. It is nevertheless challenging, partially due to large variations in pose within and across different actions and difficulty in obtaining accurate 3D motion. In this paper, we propose a Bayesian adversarial inference framework on top of a generative probabilistic model for human motion synthesis. A set of quantitative metrics are adapted and used to evaluate the synthesis quality. There are abundant prior work on this topic. Please see our paper for more discussion on related work. We begin by describing hidden semi-Markov model. In this graph, the circle nodes are random variables. The square nodes are parameters. The dynamics of time series X is modeled by hidden state Z, whose transition over time is further modeled by duration state D. The model is specified by 4 distributions, namely initial, transition, duration, and emission probabilities. Despite the improvement on modeling dynamics compared to a hidden Markov model, HSMM may still have limited capacity since we assume a single set of parameters can describe all the variations in data. We extend HSMM by treating parameters as random variables. For each parameter, it is assigned with some prior distribution defined by hyperparameters as shown in the diamond nodes. Parameters can now vary with data, thus the model capacity is increased significantly. We now describe the adversarial learning process. Our model is used as generator, which can synthesize pose sequence as indicated in the green box. The discriminative model is in the red box, consists of a set of proposed models in order to distinguish the type of action. Notice we use entropy as the output of discriminator. The entropy should be low if the data looks realistic. This is a stronger requirement that will force the generator not only produce realistic pose, but also meaningful sequence. Training such model is nonetheless difficult, with one issue being mode collapsing. To address this issue, we propose a Bayesian inference approach. Instead of estimating fixed value parameters, we infer the posterior distribution of the parameters given data and hyperparameters. At a high level, the adversarial learning objective corresponds to the likelihood. The idea was first proposed by Secchi and Wilson for GAN training. Here is a graphical model representation of the framework. Theta and phi represent the parameters. X plus and X minus represent real and synthetic data. Alpha represent hyperparameters. The posterior is intractable. We use approximate inference to generate samples of theta and phi from posterior. Specifically, we alter the sampling between theta and phi. For theta, we can decompose the conditional posterior into likelihood and prior. If the synthesized data look realistic, it will have a lower entropy than a higher likelihood. Non-informative prior is used throughout the experiment. We use SGHMC to perform the posterior sampling. Similarly, we generate samples for phi conditioned on theta. Finally, given the parameters, we generate data using ancestral sampling from HSMM. Since parameters follow their posterior distribution, synthesized data will follow the posterior data distribution. For experimental evaluation, we first show qualitative results of our method on CMU and the Berkeley mocap datasets. The videos show real and synthesized data with similar actions together. More results are shown in the above figures. Each row in each cell represents the motion sequence downsampled to 5 frames. The first row shows real sequences. The second to fourth row shows synthetic sequences. We see our model can generate a realistic motion sequence with discernible pattern and a noticeable variation within same action type. For quantitative results, we evaluate fidelity, diversity, and the similarity of the synthesized data. We synthesize 1,000 sequences for computing each metric and repeat the process 10 times to get a mean and a variance. We compare with both PGM and neural network-based state-of-the-arts. The first metric is blue score adopted from NLP research. Here it measures whether a sequence of posts look meaningful, just like whether a sentence makes sense. The higher the score, the more discernible the sequence. Please see our paper for more validation. Our method achieves overall better score than other methods on the different post cardinalities. The other two metrics are inception score and the maximum mean discrepancy. IS measures diversity of the synthetic data, which is the higher the better. MMD measures the distribution level similarity to real data, which is the smaller the better. Notice the Bayesian inference approach in the second last row outperforms adversarial learning approach on both datasets and metrics. Finally, we demonstrate the benefit of fully probabilistic model in restoring missing values. Please refer to our paper for details. To summarize, we develop a probabilistic dynamic model and a Bayesian adversarial inference framework. We demonstrate the benefit of our approach in both synthesis and restoration tasks. Our future direction is developing better prior by incorporating domain knowledge and estimation from data. Thank you for watching.